Today we're going to work on taking the derivatives of trig functions. So we're going to start with the derivative of the sine of x. And of course, under the rules that we've learned so far, or the power rule, the product rule, and the quotient rule can be applied to sine of x. So we have to go back to our original method of finding derivatives, which is take a limit as h approaches 0 of the difference quotient of our function. So sine of x plus h minus sine of x all over h. And at first glance, it may seem like there's not anything we can do to simplify this down, but we need to remember back to the formulas that we learned, the sum and difference formulas that we learned for our trig functions. So sine of a plus b is equal to sine a cosine b plus cosine a sine b. And so sine of x plus h should be able to be expanded out to become sine x cosine h plus cosine x sine h. And then we still have the minus sine x up there at the top, all over h. And with any luck, we'll immediately notice that both this first term and this last term have a sine x in them. So we're going to group those two terms together and factor the sine x out of it. So this will give me a limit as h approaches 0 of the sine of x times cosine h minus 1. And I'm going to put that all over h. And then I'm going to just add to that a limit as h approaches 0 of cosine x times sine h, our middle term, all over h. And what we should be able to do here is now separate these two limits into 4 different limits. And with any luck, again, we're going to recognize that the limit as h approaches 0 of cosine h minus 1 over h is equal to 0. That's a limit that we explored way back during our limits unit. And we also recognize that the limit as h approaches 0 of sine h over h is equal to 1, another limit we looked at back in our unit on limits. So what we end up with here is 4 different limits. A limit as h approaches 0 of sine x times a limit as h approaches 0 of cosine h minus 1 over h plus a limit as h approaches 0 of cosine x times a limit as h approaches 0 of sine of h over h. And from there, as we said a minute ago, we should be able to evaluate 2 of these limits. And the other 2 should be pretty straightforward. As h approaches 0, sine x is just sine x. So we end up with sine of x times the limit as h approaches 0 of cosine h minus 1 over h, which is 0, plus the limit as h approaches 0 of cosine x is just cosine x, and the limit as h approaches 0 of sine h over h is just 1. So that leaves us to find that the derivative of sine x is just cosine of x. And because 0 times sine x is 0, and 1 times cosine x is cosine. So now we've got a proof here using limits that the derivative of sine is cosine. This is a derivative rule that you're going to need to memorize. We're going to use it over and over and over and over again. So we have 6 different trig functions, and we're going to have to come up with derivatives for all 6 of them. So our next one is going to be to take the derivative of cosine of x. And so this is going to start out as a limit as h approaches 0 of cosine of x plus h minus cosine of x all over h. And we're going to then use that same exact type of formula that we used a bit ago, sine of x plus h, except this time we're going to use the one for cosine of x plus h. So if you don't know the formula for that, you can look up the sum formula for cosine, but it should come out to be a limit as h approaches 0 of, and then cosine x plus h is equivalent to cosine x cosine h minus sine x sine h. And then we have that minus cosine x at the end, all over h. And just for the heck of it, we'll write this up here as cosine of a plus b is cosine a cosine b minus sine a. That didn't look very good there. Sine a sine b. If that's the rule we use, cosine a plus b is cosine a cosine b minus sine a sine b. So cosine x plus h is cosine a cosine h minus sine sine h. And we'll do the same thing we did previously, as we'll group the first and the third terms. Both have a cosine x in them. This becomes a limit as h approaches 0 of cosine x times cosine of h minus 1 all over h. And we'll now subtract this time a limit as h approaches 0 of sine x sine h over h. And we should, I think, recognize that we're going to split this up into 4 limits. One is h approaching 0 of just cosine x. The next one will be a limit as h approaches 0 of cosine h minus 1 over h, minus a limit as h approaches 0 of sine x times a limit as h approaches 0 of sine h over h. And over here, as h approaches 0, cosine x is just cosine. And as h approaches 0, cosine h minus 1 over h is a known limit that we proved in the limits unit. That's 0. And then we have minus the limit as h approaches 0 of sine x. Since there's no h in there, that is just sine x. And then as h approaches 0, sine h over h is another limit we proved in the limits unit. That's 1. And we end up with the derivative of cosine is negative sine of x. So 2 out of 6 done. 1/3 of the way there. We need to find the derivative of tangent. So we might be tempted to follow the same process we've been following, right? Tangent of x's derivative should be a limit as h approaches 0 of tangent x plus h minus tangent x over h. But that's not going to be as efficient as rewriting tangent as sine of x over the cosine of x. And if I have sine x over cosine x that I'm looking for the derivative of, I just have to treat that as a derivative using the quotient rule, right? This is u over v. So the derivative of tangent x is the derivative of sine x over cosine x, which is v, our denominator, times our derivative of our numerator. And we now know that the derivative of sine is cosine. So we have cosine x times cosine x. And then we've got minus. So that's our v and our du. And we got minus our u, which our u is going to be sine x. And then our dv is going to be the derivative of cosine x, which we now know the derivative of cosine is negative sine x. And we're going to put that all over the denominator, v cosine x squared. And if we simplify this down, we'll end up with cosine squared x plus sine squared x in the numerator, all over cosine squared x And hopefully you remember back to your Pythagorean trig identities that cosine squared x plus sine squared x is equal to 1. So we have 1 over cosine squared x. And traditionally, we'll write the derivative of tangent x, secant squared of x. So now we've got our third one. The derivative of tangent is secant squared. You need to memorize all 6 of these once we get them all done. Our next one is going to be the derivative of secant of x. We have to come up with a way to rewrite secant in terms of sine, cosine, or tangent, because those are the 3 trig functions we know the derivatives of. So the derivative of secant is the same as the derivative of 1 over cosine x. Well, 1 over cosine x actually looks like a reciprocal rule problem. So we can use the reciprocal rule. The reciprocal rule says keep the constant up in the top, which is 1, and then put a negative sign, and then take the derivative of the denominator. The derivative of cosine is negative sine, and then divide that by the cosine squared of x, right? The denominator squared. So this just gives us sine x over cosine squared x. And traditionally, that's not how we write the derivative of secant, although this would be perfectly acceptable if you did keep it that way. We'll break this down into 1 over cosine x times sine x over cosine x, which is secant x times tangent x. And that's the traditional way that we'll write the derivative of secant x, although sine x over cosine squared x is fine as well if you want to do it. Probably memorize it as secant x. Our next one is cosecant of x, which we'll rewrite as a derivative of 1 over sine x. And we'll follow that same rule, the reciprocal rule. So our derivative of 1 over sine x should be negative, and then derivative of the denominator, using the reciprocal rule, so negative cosine x divided by the denominator squared. Right? That's just the reciprocal rule. So we can rewrite this as negative 1 over sine x times cosine x over sine x if we want to. And this is normally how it'll be written, is negative cosecant x times cotangent x. And that's our derivative of cosecant x that you'll need to memorize. And our last one, the only one we've got left here, is the derivative of cotangent x. And we've got 2 different ways we can think about the derivative of cotangent x. The first would be to take the derivative of 1 over tangent x and use the reciprocal rule. So that would be negative derivative of tangent. Derivative of tangent is secant squared. And then we would divide that by tangent squared. And we should be able to simplify that down a bit. Negative secant is negative 1 over cosine squared x. And tangent squared is sine squared x over cosine squared x. And anytime you have a complex fraction where the denominators are the same in both the numerator and the denominator, so we've got cosine squared here and cosine squared here in the denominators of both parts of our fraction, we can just eliminate those and turn this into negative 1 over sine squared x, or negative cosecant squared x. So our derivative of cotangent is negative cosecant squared. And of course, we could do this another way. We could also rewrite this as a derivative of cosine x divided by sine x. And then we could use the quotient rule. We should see that we'll come up with the exact same answer in the end as we did using the reciprocal rule. So the quotient rule says denominator times the derivative of the numerator, which is the derivative of cosine, which is negative sine x, and then minus our numerator, cosine x, times our derivative of our denominator, derivative of sine x is cosine x. And then we'll divide it all by the denominator squared. And we should simplify this down to negative sine squared x minus cosine squared x over sine squared x. And if we take a negative 1 out of the numerator, we get negative 1 times sine squared plus cosine squared over sine squared x. And since we know that sine squared x plus cosine squared x is 1, we now have negative 1 over sine squared x, or negative cosecant squared x. So either way you go about it, you end up with the exact same derivative. And so here are all 6 of our trig derivatives. You definitely need to commit all 6 of these to memory. And if you don't memorize these derivatives, you are going to have a very difficult time making your way through this unit on derivatives. So now that we know these derivatives, let's take a few minutes and see if we can apply some of the rules that we already know, like the product rule, the quotient rule, maybe the power rule, to some derivatives that involve trig functions. So here we've got the derivative, we're looking for the derivative of f of x equals tangent x over x. So this is a quotient of 2 functions. This is u over v. So we'll use the quotient rule, which says v times the derivative of u, and the derivative of tangent x is secant squared x. So v du minus u times dv. And the derivative of x is just 1, so I don't need to write that. So this is v du minus u and dv of 1 all over the denominator squared. And it's that simple. There's no other simplification to do with that. That's it. For secant x over sine x, we'll again use the quotient rule. This is again u over v. So we'll take a look at it as if we're going to take a derivative with the quotient rule. It's sine x v times the derivative of u, and the derivative of secant is secant x tangent x. So v du minus u dv. So minus secant x, and then the derivative of sine x is cosine x, all over the derivative of sine, not the derivative of sine, but the sine squared. And we can simplify this down a bit, I would think. If we have sine x and secant x, right, sine x times secant x is the same as sine x times 1 over cosine x, which would be sine over cosine, which would be tangent. So we've got a tangent x from these 2 terms here. And then times another tangent x would be tangent squared x. So we've got tangent squared x minus, and then secant times cosine, that's 1 over cosine times cosine, which would just be 1. So we have tangent squared x minus 1 over sine squared x. And that's it. We want to find the derivative of secant squared x. This isn't currently set up for one of the rules that we would normally use, the product rule or the quotient rule. But we should know that secant squared x is the same as secant x times secant x. And we can now use the product rule. Product rule says the first function, secant x, times the derivative of the second function, and the derivative of secant is secant x tangent x, plus the second function, secant x, times the derivative of the first function, which we know the derivative of secant is secant x tangent x. So we just end up with two of these, two secant x's times secant x tangent x. Or two, since we have secant times secant, two secant squared x tangent x. And this is a perfectly good and acceptable answer. If we wanted to find the first four derivatives of sine x, we should be able to do that. And maybe note some interesting properties of sine. The first derivative of sine x, we know, right? The first derivative of sine is just cosine. And we should know the derivative of that. Our second derivative for sine is the derivative of cosine, which is negative sine of x. Well, our third derivative should be the derivative of negative sine. Well, when we take the derivative of sine with a constant out in front, just keep the constant, -1, and multiply it by the derivative of sine, so negative cosine. And our fourth derivative of x, well, keep the negative sign and multiply by the derivative of cosine, which is negative sine, giving us the fourth derivative of sine x is just sine x. And we could go through and say, well, the fifth derivative must be cosine, the sixth must be negative sine, the seventh negative cosine, and the eighth would be back to sine. So any multiple of 4 on a derivative of sine is just going to go right back to sine of x. If I asked you for the 100th derivative of sine, well, since 100 is a multiple of 4, must be sine x. If we're looking for the second derivative of secant, we'll first need the first derivative. F prime of x is going to equal secant x tangent x. And then to find our second derivative, all we need to do is use the product rule to take the derivative of this. So f double prime of x is the first function, secant x, times the derivative of the second function, and the derivative of tangent is secant squared x. So u times dv plus v times du. And the derivative of secant x is secant x tangent x. So looks like we end up with secant cubed x plus secant x tangent squared x, which is perfectly acceptable. Or if you want to factor a secant x out of it, you could have secant x times secant squared x plus tangent squared x. There's lots of different ways to manipulate these around. It doesn't really matter what form you leave it in. What's important is that you are knowledgeable about your trig identities and you can manipulate these around into any form you need it. Sometimes a multiple choice question on the AP test might have one or the other of those, or it might turn those into sines and cosines, or it might use a diagonal trig identity to turn tangents into secants or secants into tangents. So you just need to be aware of the trig identities and be able to manipulate your answers into whatever form you might need. Here we're looking at a derivative of two different trig expressions being multiplied together. So we have two options here. The first option is treat this as if it was u and v, and use the product rule, because that would be u times v. And there's nothing wrong with that, except that it's kind of messy. And it's usually best to try and simplify any trig expressions that you have before you try and take a derivative. So I would just distribute all this out. Cotangent x times tangent x. Well, cotangent is 1 over tangent, so that's like tangent over tangent. That's just 1. So f of x is going to start off as 1. And then we've got cotangent times sine of x. So that's like cosine of x over sine of x times sine of x. Well, the sine x's should cancel, and we'll just be left with cosine of x. And since we had a negative there, it'll be minus a cosine. Then we'll do the cosecant times the tangent. Well, cosecant is 1 over sine, and tangent is sine over cosine. That gives us 1 over cosine. And 1 over cosine is just secant. And then we've got cosecant of x times negative sine of x. Well, cosecant is just 1 over sine. So we have 1 over sine times negative sine. That should cancel out and just become a negative 1. So really, f of x is really just a secant x minus a cosine x. Right? The 1's cancel out, which tells us that f prime of x should be the derivative of secant, which is secant x tangent x, minus the derivative of cosine. Well, the derivative of cosine is negative sine. So minus a negative sine should be plus sine x. And there's our derivative, secant x tangent x plus sine x. So we'll just do one more of these today. We're going to find the derivative of sine x over 1 plus cosine x. And there's no simplification we can really do here to begin with. So we'll just treat this like u over v using the quotient rule. So our derivative, f prime of x, ought to be v, 1 plus cosine x, times du, derivative of sine x is cosine x. So v du minus u sine x times dv. Well, the derivative of 1 is 0, and the derivative of cosine is negative sine. And then all over v squared. And now we'll do a little bit of simplification here. If I distribute out this 1 plus cosine x with the cosine x, we end up with cosine x plus cosine squared x. And a negative sign times a negative sign is a positive sign, squared x, all over 1 plus cosine x squared. And we'll think back to our Pythagorean trig identities. We know sine squared x plus cosine squared x is equal to 1. So we now have 1 plus cosine x divided by 1 plus cosine of x squared, which should just give us 1 over 1 plus cosine of x. And that's going to be it for today. We've now got derivatives for all 6 of the trig functions. We know the derivative of a constant is 0. We've got the power rule to deal with x to the 2nd or 3rd or 1/2 power or negative 5th power. And we've got the product and the quotient rules to deal with when we have 2 functions being multiplied or divided by each other. The next time what we're going to look at is what happens when we have a composition of functions, when we have f of g of x, and how to take those derivatives. And that's going to really expand out the options for the types of functions that we'll be able to find derivatives. But that's for next time. That's called the chain rule. So we'll do the chain rule next time. And then we're going to add in after that a bunch more derivatives of functions like exponential and logarithmic and inverse trig functions. That's it for today.